G'day everyone, welcome to Lubrication Explained, and in today we're going to do a slightly different video. It's going to be a longer format where I'm going to take some raw data from used oil analysis results of an engine fleet, specifically one that's running on landfill gas, and we're going to look at the different ways that we can analyze and sort of cut the data to give us some better insights than we would typically see just by viewing the reports one by one. Now, there is going to be a little bit of information that is specific to engines that run on landfill gas. However, all the techniques that I'm going to show you here can be applied really to any kind of engine oil analysis. So whether that's diesel, petrol engines, natural gas, biogas, etc. So as we run through, I'll talk about some of the important things to look out for, a few tips, and hopefully by the end you'll kind of understand the workflow and the process, and you'll be able to use it at your own plants as well. I'm going to approach this from the perspective of a let's say a maintenance engineer, someone who is looking basically for three things. They want insights into oil degradation mechanisms, which will inform them whether they can extend oil life. And of course, the third thing that they'll want to know is what is the status of the engine itself? So is it experiencing any kind of adverse wear? Because that will be a limit on how far we can extend the oil life. Right? So this is an exercise in trying to preserve the oil to save money and trying to preserve the equipment to also save money and minimize oil changes and interventions. So where we're going to start is this data, right? So I'm showing an Excel spreadsheet. I'm going to do everything in Excel here, so there's no specialized knowledge required. Basically, everyone has access to some version of Excel because there is an Excel online as well. You can pretty much do this in any kind of processing application, but obviously Excel is the most commonly used one around the world, so that's why I'm going to use it. Now, where this data comes from, your used oil analysis provider, whether it's an ALS or an SGS or a Bureau Veritas, Oil Check, Wear Check, whoever it is, they will be doing oil analysis samples and they'll be testing them, and all of the raw data goes into a back-end system. So it might be an SQL database or something like that, where it's all stored for extended periods of time. You, as the client, can usually request through a web portal for an export of all that data, and it usually will come to you either as an Excel file or as a CSV file, which you can open in Excel. So this, what I'm showing you now, is the raw data that I would have got out. I've cleaned it up a little bit because there are some fields which are not going to be relevant to us, right? So as an example, there was a column in here for Carl Fisher water, but they didn't do that because it's not on the slate for a biogas engine. Sorry, a landfill gas engine. So I've cleaned up the data a little bit so that we can see it a little bit better. I'm also going to zoom in a little bit just so that you can see it a little bit better. If people are watching this on a phone or a tablet, it is going to be quite hard to see this little text, but hopefully you can get an idea for the steps as I go along. Now, the first thing that we want to do when we have all this raw data is to really kind of take a look at what's going to be important to us. First of all, just in the view, I generally like to freeze the top row, right? So that means that when I'm scrolling, the top row will stay the same. I might also format that so I can just see it a little bit better. So I'll make some white text on a grey background. Yeah, there we go. Okay, so now I can see those as I go along. The other thing I'm going to do is I'm going to look at what I think are going to be the important columns that I'm really interested in. For example, compartment type, the fact that this is a gas engine is going to remain the same for all of the different samples. This fleet was running 3 separate engines that were all Jenbacher J320 engines, right? So they're all the same make and model. So I really don't need to know about the compartment type, make, and name. Okay, so we'll just hide those. We've got sample dates. I might want to know that, whether the fluid was changed or not, diagnosis, okay, and then we come along to some of these fields. Okay, so some of the important ones are going to be the age of the oil. So I'm actually going to highlight that so that we can easily find that. The date that it was sampled is probably going to be important. The type of fluid. So over this data, there are actually 3 different oils that we used over the course of about 3 years. So maybe one of the questions we want to answer is which one preserves the engines the best, or which one degrades the slowest. So we might want to do a comparison of different products. What else have we got here? Okay, some of the more important parameters. KV100, right? So that's the viscosity at 100 degrees Celsius. That is the most important parameter for lubrication, right? So it's all about viscosity, viscosity, viscosity. We might also want to understand calcium, because that's going to be related to the TBN. That's an additive. Magnesium, not so much. Definitely oxidation, because that's a really important marker of oil degradation. We'll want to understand the PQ index, right? Because that's going to talk about wear. Might want to understand phosphorus, because that's an additive. Nitration, there was no nitration in any of these engines. The reality is these engines didn't run kind of long enough to experience nitration. And in most modern gas engines, nitration is not really that much of a problem. We probably want to understand lead, right? Because that will relate to bearing degradation. We'll definitely want to understand TAN as well as TBN. Okay. What else do we want to know? KV at 40. So that's viscosity at 40 degrees Celsius. We might want to have a look at that, but the reality is that for gas engines, they tend to monitor at 100 degrees Celsius. We'll also want to understand aluminium, because that's related to piston and liner wear. And we'll want to understand copper, because again, big and small end bearings. Zinc will probably relate to the additive package, and we definitely want to understand iron, because the rate of iron degradation is really important to most of the components in the engine. The last one that we might want to know about is silicon. Now that's something that is probably a little bit more specific to the biogas and landfill gas market. So if any of you have heard of siloxanes, these are components that are present in a lot of modern day household cleaning products and cosmetics as well. And what happens is that as they degrade in the landfill, they end up in the process gas, and in the combustion chamber, those siloxanes turn into silica, which can be really damaging to the engine because it's effectively sand. Very, very abrasive. All right, so now that we've kind of got all of that packaged up, next thing I want to do, right, is I want to see if I can easily view the data. Now, some people really like to use pivot tables, right? So, which I'll try and put in a new worksheet. But as it happens, this data isn't really formatted in a way that is conducive to using pivot tables, right? So, rather than going through the exercise of trying to clean it up, what I might do instead is just create some new sheets which are filtered by what I want to look at. So, as an example, right? Let's copy and paste all this data and create a few different versions. So if you'll remember, we might want to compare the 3 different types of oils. Okay, so let's create 3 different copies of this initial data workbook. Right, so making sure I always create a copy. Okay, and I'm going to call these, let me just reorganize them. I'm going to rename them. This one is going to be oil A. This one is going to be oil B. And this last one is going to be oil C. All right, so in each of these ones, what I'm going to do is organize the data. So I'm going to filter, right? And I'm going to filter by fluid, right? So in this case, I only want oil A. In this instance, again, filter the data. I only want oil B. And in this instance, I only want, again, to filter the data by oil C. All right. Now, I'm doing this blind, so I actually don't know what each of those fluids are. I don't know the brands or anything like that. So we're going to try and keep this completely brand agnostic. I'm not trying to rag on any particular type of engine oil. All right. Now that we've done that, we might want to start exploring the data a little bit. So, for example, let's start with an analysis of viscosity at 100 degrees Celsius. And I'm going to put that in a new tab, which I'm going to call charts. Right, so I'm going to insert, it's always going to be a scatter plot. And I prefer them just to have laid out like this. Okay, and we're going to select the data. I'm going to add a series. Now the first thing is I'm going to do it for the 3 different oils, right? So I'm going to call the first one oil A. The series X values, so on the X-axis we're going to put the age of the fluid, right? And on the Y-axis we're going to put, we are going to put the KV100 value, which was over here. Okay, now I'm going to edit that data because it really needs to go from number 2, 2 to, let's say, 1,000, or let's make it 2 to Okay, and I also want to change the chart design, right? I'm going to change the chart type so that it's just dots. Okay, so that is the viscosity of oil A. Now I want to get the formatting of this one right because we're going to just copy and paste a whole bunch of different versions of these. So I'm not a huge fan of all of these lines. Let's get rid of those so it's a little bit cleaner. Okay, we're going up to 1600 oil hours. That probably doesn't need to be the case. Let's change that to 1400 because we don't have anything above that. All right, so this is for oil A, and I'm also going to put in as a quick layout like this. We'll change this to KV100 as a title, and along the bottom we've got oil hours. Okay, now we want to add the data for the other oils, right? So we can get a comparison of the viscosity degradation. So again, I can select the data. I'm going to just copy this because I'm going to use that. Okay, all right. So I want to add another data series, which this time we're going to call oil B. The series X values are the same because the sheets are identical. I'm just going to rename that. And again, and change this. Actually, so this is in sheet oil B, and we wanted the KV100 again. All right, so what you can see there already is that oil B has a slightly higher viscosity than oil A, and it's consistently higher. Finally, we'll add oil C, right? And in oil C, once again, we'll go across to the KV100. All right, so now our chart is complete. Again, I'll get rid of these lines, and because there are no results below 12, I'm going to change the axis options so that it has a minimum of 12. Right, now you can see the spread. What's interesting about this is that you can already see that oil A has a much more stable viscosity than the other 2 oils. Right, now that's not necessarily a good thing, okay? Because we need to take it in context with the different limit values. So I have the document for Jenbacher's limits on their oil analysis program. And one thing that you can see is that the viscosity at 100 degrees Celsius is okay so long as we remain below 17 centistokes, right? Now I've actually taken this document, right? So it has limits for viscosity, tan, TBN, oxidation, nitration, contaminants, and metallic elements. And I've actually summarized this in a different sheet over here, which I've called alarms. So we're going to use those in a little bit. But what you can see first of all from the charts is that for KV100, right, everything remains below 17, so we are significantly below the limit, and so that all looks okay. Right, now we might want to compare, for example, TBN stability, right? So, well, sorry, actually, let's start with oxidation, because that's most heavily related, right, to KV100. We expect that in use, the oil will oxidize. And so oil oxidation is the second most important parameter. One thing I might do actually so that we can see the points a little bit better is I might just reformat these. So, whoops, hang on. I'm going to format the data series, and I'm going to say that the markers have no fill, right? I'll make them transparent. So those ones can be blue. These ones I might make, whoops, make them no fill, but make the border red. And for these ones, I might make it no fill and a border that's green. All right, so now we have, that's well, now I'm going to change, all I have to do now is, because the x-axis is going to stay the same, all I need to do is change the y-axis values. So what I need to do is scroll across to oxidation, which is AQ, right, and change that single letter, and it will update the chart for me. And I'll do that on all three of the different data sets. So I am going through this pretty quick, but again, if you need to, you can pause. I'm going to resize this axis because it no longer has a minimum of 12, and there you go. So this is oxidation. Now this is a really interesting one, okay? So oxidation, the recommendation for the Inio-Yenbacher limits is, you can see up here, right? I'll scroll in a little bit more. So oxidation can go up to 20, right? So 20 is the limit. However, if we look at these oxidation curves, one thing that's striking is that new oil does not start at 0 oxidation. Why could that be? Well, it's very common for third-party oil analysis labs to use a test method which is called the JOAP method. Also, sometimes you'll see it as, I think it's ASTM 2412 Annex B, no, Annex A, which would be it's called the direct method of oxidation testing. Now, Yenbacher, in their document, specifies a guideline, which is ISO 51453. That is called oxidation by differential spectra method. What differential spectra does is it has a reference spectrum for new oil, then you get the spectrum for old oil or used oil, and it subtracts one from the other. So in this guideline that Yenbacher has stated, oxidation should always start at 0 for new oil. So what does that mean? It means that even though we might have results above 20, this is not, right, the same used oil analysis test that is being applied, right? So in some ways, it's not so relevant. So we can, in some ways, ignore the oxidation, but we can see, so we'll ignore the absolute value, but we can observe the degradation pattern. And in most of these cases, it looks like basically a straight line, right? But the oxidation is not increasing severely. So that's a good sign. And it's also reflected in the KV100 value, which is not changing all that much. Okay. All right, we know that there's not really any nitration, so we'll ignore that. And what's next most obviously related to oxidation is tan. Okay, so we'll create again another one of these. Now remember I said that the tan TBN crossover is really not that relevant, but some people still do think it is, which is kind of interesting. But I'm going to put them on different charts because tan and TBN, as I have explained in a different video, are completely different entities. They're not really all that related. So again, what I'm going to do is I'm going to do this the easy way, which is to go and find tan. So tan is BA on the y-axis. Okay, and I'll change that for all of them. All right. For some reason, why did oil C change color? I wanted you to be red. Oops. Why did it do that? Anyway, let's just leave it for the moment. Okay, now this is interesting because the tan degradation appears quite different, right, across the different oils. Now, this is something where it gets really interesting when you consider landfill gas engines, because what you can see is that oxidation produces organic acids, and therefore, especially in a natural gas engine, oxidation and tan will track with each other, because oxidation is going to produce organic acids which contribute to the acid number. In landfill gas, we have an additional contribution which is not related to the oxidation. So we have oxidation producing organic acids, but we have landfill contaminants producing strong acids, strong mineral acids. So as an example, if you have H2S in your fuel gas, when the H2S is combusted, it forms sulfates, so SO2, for example. And when that gets into the water in the crankcase, that dissociates and becomes H2SO4, which is sulfuric acid. Same with chlorine in landfill gas. Chlorine will eventually form hydrochloric acid, which is another strong mineral acid. They are contributors to tan, right? So that's why in this instance, tan doesn't necessarily track with TBN in the same way. All right, so tan doesn't track with oxidation. Let's also look at TBN, because tan and TBN are related, right? No question that they're related. However, they're not related in the way that you think. So let's look at TBN. Now, I think it'll be interesting to see here. I suspect that the oils will have different starting TBNs. All right, so again, where's TBN? TBN is BC. Whoop. And oil C. All right. So a couple of things that we can determine. First of all, the starting TBN of oil B is much higher than the other two. Oil B, which is the green one. Oil C, which is this one in grey, which keeps turning grey for some reason, and then turns everything grey. Why is it doing that? Let's just check that our data filter has been applied correctly here. It has? Okay. Weird. Okay. Well, it's going to stay grey for the moment. Okay, so oil B starts with a much higher TBN, and oil B is the green one. Now, what you can see is, although it has a much higher starting TBN, that doesn't necessarily mean that the acid increase is any different to the other oils, right? So remember, TBN, the reason why TBN and tan are different is because base number is an additive, right? The oil suppliers put over-based detergents into the lubricant to help neutralize acid buildup, right? That's why it's there. So the acids are going to be, in some ways, produced no matter what, right? So they're strong acids, and organic acids are going to be produced no matter what. You can't do anything to stop that. What TBN is supposed to do is then neutralize those acids. So TBN and TAN will be related, right? Because TBN is supposed to help flatten out TAN and reduce it. However, TBN is an additive, whereas TAN is a byproduct of oil degradation and contaminants, right? And that's why I don't like to sort of conflate the two with each other. All right, so that's TBN. Now remember that if you remember on the Jenbacher document, which I'll go back to, the limit for TBN, okay, is actually dependent on the fresh oil value, and same with the acid number. So what they say is, what is the starting TBN? You need to condemn your oil when it gets to 50% of that number. So the alarm limits for each of these different lubricants is actually going to be entirely different. So oil A, which is in blue, starts off at about 7. So it should be condemned when it gets to about 3.5, which is, on this chart, at about 1,000 hours. Whereas oil B has a much higher starting TBN of around 10, which means that you would need to condemn it around 5. Right? So although it appears to have a higher TBN, right, you would actually condemn that oil earlier. So you would get less oil life if you are obeying the Jenbacher limits. Right? So it's not all about absolute value, it's about the relative value to the very beginning. All right. Now, let's also look at some of the wear metals as well, right? Because they are going to be important to us. So specifically what we want to look at is the iron. Iron's the most important, followed probably by aluminium. So let's look at those. Okay, so iron, where is it? It would usually be somewhere along here. Okay, BT. I'm going to rename this one iron. Now the good news for us, right, is that iron is staying relatively low. So the Jenbacher limit for iron is 20 parts per million. Now I have problems with that limit because the reality is that you shouldn't care about the absolute value of iron, you should care about the rate of deposition in the oil, right, because that's related to the rate of wear. But that's a disagreement that I have with the OEMs. Now, iron, you know, the limit for Jenbacher is 20, so you can see that we're nowhere near the limit, right, for iron. And I would expect that we'll see exactly the same for aluminium. So this tracks well, right? What it says is, because our viscosity is in line with what the OEMs require, right, that means that supposedly we should be getting sufficient wear protection out of our engine oil, and that is reflected in the wear metals. Great sign, right? So that is a good sign. So let's just quickly check aluminium. And I'm going to change the data here, right, again to show aluminium, which is in column BH. Okay, so hopefully you're starting to get the feel that you can build a lot of these charts very quickly, but we also want to apply some knowledge that we have about lubricant technology, because without that understanding, they sort of don't really mean anything. And again, aluminium is also staying really low, and the limit for that one is, I think, 15. Did I put it in here? Yeah, I did. So the aluminium limit is 15. Right? All right. So that's good, right? Iron and aluminium are tracking quite low. Now, here's the thing. Let me get to why this site condemns their oil. So at the moment, we're not seeing any reason why you would actually junk this oil. I'm about to show you why. I'm about to show you how this particular site could save a hell of a lot of money. All right, so let's select this data and change this to silicon. right? So silicon is Cb. All right, so the limit for silicon, as dictated by Jenbacher, is that you must condemn the oil when the silicon value gets to 200. Now, why are there two different silicon limits? Okay, so Class A fuel gas is natural gas. Right? So if you're operating on natural gas, that means you're using a natural gas engine oil, which means that you can only go up to 20 parts per million. But if you are operating on Class B, which is biogas, or Class C, which is landfill gas, you are permitted to go up to about 200 parts per million. And that's because the landfill gas engine oils are formulated to cope with siloxanes. Okay. So what you can see here is, here's the limit of 200. And basically, as soon as they see a result that's above 200, they change the oil. Okay. Now that makes perfect sense for this site as to why they would do it. They are simply abiding by exactly what the OEM has stated, right? So if you see ICP get silicon above 200, you must condemn the oil. Now I should stress, if your engines are in warranty, you have to obey the OEM limits. Otherwise, your warranty is junk. Okay. However, once your engine and all its components gets beyond its warranty period, these become guidelines, right? So you don't have to obey the letter of the law for the OEMs. Obviously check that with your supplier first, because you may have some parts that are in the engine which are in warranty. You wouldn't want to avoid that. Okay, so now let's have a little bit of a think about silicon. Why is silicon important? Remember what I said before. Silicon comes from siloxanes, which are in the landfill. Siloxanes, when they get into the combustion chamber, turn into silica, which is very abrasive. So the reason that I care about silicon is because it will cause engine wear. But hang on a second. We just showed that the engines are not experiencing severe wear. Right? So, what does that say? What that says is, we could probably look at the relationship between abrasive siloxanes and abrasive wear to see how severe is it. So let's do that, right? So what we're going to do here is we're going to put silicon on the x-axis, right? So as it goes from 0 to 200, and see what happens to iron, right? Now to clean it up, let's go, okay, so first of all, that means that the y-axis has to be H, right? And the x-axis needs to be iron, which was, where is that? Iron was BT. Again, BT, BT, H, H. Right, so this is us kind of taking it one step further, right? We want to, so this is no longer oil hours, this is silicon, right? And we're going to change this axis, right, to a maximum. Oh, hang on. I've done that the wrong way around, apparently. Oh, my fault. Let me change this. So this here is going to be, I need that to be silicon. My fault, hang on. So actually I want BT on the y-axis, and I want silicon, silly me, which was right at the end here. Silicon is CB. Okay, so CB and BT. Last one. CB, BT, BT. All right, that looks better. Okay, so what we can see is, as we get to a value of 200, we're condemning the oil, and yet iron, which is on the y-axis, is nowhere near the limit. So if we wanted to show, let's say that we were using oil A, right? And we wanted to say how far, how much silicon could we handle before we get to the OEM limit for iron, right? So what we want to do is, this appears to be kind of linear in its increase. And I'm going to forecast forward by another 300 hours, right? And what you can see is iron is still only projected to be 10 parts per million. So now I'm going to forward 600 hours, 16 parts per million, 900 hours. We finally get to 20. So what this is saying is, right, we are condemning our oil at 200 parts per million. And that is getting us at about 1,000 oil hours. Realistically, we are being way too conservative. We could go to 1,200 hours. And at that point, we are projecting that that's when our iron would get to 20. Now, in practice, would you let your oil go to 1,200 hours? No, right? Because at that point, your TBN would be junked, right? And we'd have to watch our iron very carefully because we're assuming a linear increase here, and it could start to increase at a faster rate, right? So it may be that we could only get to a silicon value of 600. But silicon deposition in the engine oil is at a fixed rate, right? It's dependent on the landfill gas. So what this is saying is we are currently getting an oil life of about 1,000 hours, right? And that's when the silicon gets to 200. Realistically, we could let our silicon get to 600, which would give us 3,000 oil hours. Now, for a site that is running, in this case, this trial was done on 3 engines, but there are actually 14 engines on site. Being able to extend your oil life by a factor of 200% would make a huge difference to your bottom line. Not to mention the fact that this site is remote, and so you need to send maintenance techs out there much less frequently, right? So this is, a really exciting insight for these guys. Now, so that is silicon, right, as it relates to engine hours. So again, right, all we've done is taken raw data, right, plotted up in a few charts, and even then, we have, in this very short space of time, I think I've been talking for about 40 minutes, been able to demonstrate significant savings. And this is the power of oil analysis, and this is why I think it's so undervalued, right? Because everyone out there is doing oil analysis, but no one is actually going back and looking at the data. Now, this is just step one, right? I would love to talk about more advanced data analytics and machine learning techniques, but I might have to leave that for a future video. So anyway, I hope that you have kind of enjoyed this little tutorial, this kind of webinar. If you've got questions and comments, please leave them below. I'd love some feedback on this layout as well. So this is a different kind of video to what I usually would do, much longer format, and probably a little bit more niche. There's probably only a couple of people who are going to find this useful. But if you're one of those people and you want to see more examples like this, you're even welcome to send me your used oil analysis data, and I can analyze it for you. I think there's some really great case studies to be had out there. So anyway, I hope this has been fun. As usual, this has been, well, let's call this Lubrication Explored, because we probably explored lubricant data in a way that we don't usually typically explain. But yeah, we'll see you next time. Thanks.